Very good morning to all. As we are all aware, today we are having one important topic related with Kibble balance. As we are aware, since 2019, the artifacts of all these physical constants have been changed in universal constants. For example, for mass, realization of mass, we are using Planck's constant h, which is a constant value, universally constant. We have with us Professor Dr. Nidhi Singh. She is a senior principal scientist and heading mass metrology subdivision of CSIR NPL. She works in the area of mass, volume, density, and viscosity. She is involved in development of Kibble balance at NPL. In addition, her research interest she also include mechanical properties of high temperature titanium alloys, rare earth free permanent magnets. She is a qualified assessor of 17025 quality system and member of BIS committees in of weights and measures. She received her BSc and MSc in physics and PhD in metallurgical engineering from BHU. Dr. Singh joined École des Mines de Paris, Evry France, for her postdoctoral fellowship and subsequently joined as senior scientist in Division of Engineering Materials of CSIR National Physical Laboratory, New Delhi. In 2017, she joined Physico-Mechanical Metrology Division to work in mass metrology, including development of Kibble balance. She has written 4 books, chapters, more than 70 papers in SCI journals and conferences. She has US patent in her name and guide masters and PhD students as professor in Academy of Science and Innovative Research at ACCSIR. Thank you very much, ma'am, for accepting our request and delivering this talk on this very important topic, which is related with every meteorologist working in the country. And as we are all aware, mass is the fundamental unit for many of the, or the base unit for many of the derived units. So it is very important. And I know that you are also having a robotic mass comparator, volumetric mass comparator, a lot of very good facilities, state-of-art facilities we have at National Physical Laboratory in India. It is our apex body, which is involved in maintaining the traceability of all physical constants. Thank you very much for accepting our request. Thank you. We have with us our Honorable Shri B.N. Dikshit, Director Legal Metrology. Sir, would you like to speak 2 words, please?
Yes, please. Yes, please. So, Sri Ashutosh Agrawal ji, Director Legal Metrology, Government of India. Professor Nidhi Singh ji, the expert of the today program and the expert in the mass metrology, looking after the new topic and project Kibble balances, where she will go towards the true value of the mass, near to the true value of mass of 1 kg or whatever, 1 gram or 100 gram, 500 gram, whatever she has made the project on which she is working where it is not known to me, she will deliver all those things in her speech. So, but it is true that she is going towards the true value of mass. If she is going towards the any true value of the mass, by which we can go to the any depth, upper side and lower side of the mass also. So that is the very, very important thing here. The SI units has been defined in the Legal Metrology Act 2009. And after that, the rule also has been made, national standards rules, legal metrology national standards rules. There the kilogram, unit of mass, kilogram, that has been defined, and has been defined as per the whatever the BIPM has taken the decisions. After that, the Department of Consumer Affairs was in contact with the National Physical Laboratory to make the Kibble balance, and that time Dr. Aswal was the director, legal and director of the National Physical Laboratory. He was very much interested, and he discussed a lot of things with the Department of Consumer Affairs. And the Department of Consumer Affairs was always insisting on that very subject. I am very glad today that the National Physical Laboratory has got that very project on the cable balance or the measurement of the mass according to the new definition. Even these things will be the fundamental units, and that will be derived as a constant, but the physical constant will be continued. And according to the physical constant, trade and transaction will continue. But from the fundamental units which has been derived, the other things, scientific work will be done there. So, so like that, whatever the unit of length, meter has been defined. So the unit of mass, kilogram also has been defined. So like that, all the things will be in the same directions. So that was the motive of the BIPM. And now India is also working on that very directions. I hope today or tomorrow, the National Physical Laboratory will get the strength to define all the things according to the BIPM. So with these words, I request uh, Dr. Nidhi Singh and Dr. Asutosh Agarwal to continue the programs. Thank you all, sir.
Thank you, sir. Thank you very much for your kind and motivating words. Thank you, sir. We are always looking towards you for this type of motivation for the development of metrology and the legal metrology in our country. Thank you very much, sir. Thank you. Good day, sir. Thank you. Over to you, ma'am. Nidhi, ma'am, please. Over to you.
So, am I audible?
Yes, very well.
Okay. So, first of all, I would like to thank Ashutosh sir and Dikshit sir, also Sanjay sir, for giving me an opportunity, this platform where I can present the work which we are doing at CSIR NPL. Kindly
Well, before
confirm.
that, I just want to interrupt. After this presentation, we will put this whole video on our YouTube channel as well as on our website. This presentation will also be available to all the participants with your kind permission, if you don't have any problem.
No, sir, no problem, no problem.
Thank you.
My
Thank you.
my slide is visible.
Yes, very well. Please.
Okay. So yeah. So thank you very much for all the kind words. So now I will start my presentation. So I will be talking about redefinition and realization of kilogram using Kibble balance, which we are pursuing in our subdivision at CSIR NPL. So my talk is going to be broadly divided into three components, where I will be talking about the definitions of kilogram, and then the present definition, which we always call it as a redefinition of kilogram, and the work which we are doing at CSIR NPL, the current status of Kibble balance. So I will be broadly talking about the history and the realization method and the current status. So before we talk about the redefinition, let us first try to understand the definition of mass, which was existing from almost past 180 years. So if we see the definition, it says that kilogram is the unit of mass. Let me just have a pointer. Yeah. So kilogram is the unit of mass, and it is equal to the mass of international prototype of kilogram. So this is the picture of international prototype of kilogram kept in BIPM. In air, 3 bell jars are there where it is kept. So you can see here first bell jar, second bell jar, and third bell jars. So and the material is platinum and iridium, height 39 mm, diameter also 39 mm. So this is our international prototype of kilogram, from where we were getting traceability throughout the world. So now this was decided in 1901 in the third meeting of CGPM, that IPK is going to be considered as the primary standard for mass for the world. Now, if we talk about the hierarchy of standard, so the international prototype of kilogram is having several copies. You can see here, there are several copies of in the top and bottom layer, you can see. So they are reference standards and working standards. They are also kept in a similar condition the way IPK is kept. Now, let us come to India, where we are having our own prototype. Being signatory of CIPM MRA, we also have our own prototype. It is also made up of platinum iridium and of same dimension, and we are also trying to maintain its upkeep as it has been done in the case of IPK. So we are also keeping it in bell jar, and it remains in the custody of Director NPL. And the identification number given to the NPL India or India's prototype is NPK 57. So in India, we are getting the traceability using NPK 57. So how it is done? So every 10 years, this prototype is carried to BIPM, and using one of these working standards, it used to get verified or recalibrated, and then after bringing it back, we are maintaining the traceability in the country. So if we come to this side of the screen, so after this working standard of BIPM, as I explained, that we are taking this a national prototype of kilogram to BIPM, where it is calibrated every 10 years. Then using this, we are calibrating our transfer standards. We have 4 transfer standards, 2 made up of nickel chromium and 2 made up of stainless steel. So we are calibrating those standards, and then using these transfer standards, we are calibrating our working standards at CSIR NPL, and then we are providing traceability to legal metrology, which is our responsibility by the Act of Parliament, that we have to provide traceability to legal metrology. And then we are also providing traceability to the laboratories, strategic sector, etc. So now I will take you back in the history of mass around maybe more than 200 years ago. So how, before we actually try to understand the redefinition or the present scenario, let us try to understand from where we started. So in the year 1791, that was the first time the kilogram was defined. And it was defined as mass of 1 liter of distilled water, and the reference temperature was given as 0 degree. So that was the first definition which was given to mass. So now let us try to understand. The first definition was fluid based. It was water based. Then in 4 years of time, it was there were problem with that because the density of water is maximum at 4 degree. So it was difficult to maintain that. The dimension was 103. So then again, the definition was changed in terms of the reference temperature. So the reference temperature was made 4 degree in 1795. So just for 4 years, that definition was there, and then the reference temperature was changed. However, maintaining a fluid-based primary standard was difficult due to several reasons, where we have like evaporation kind of thing is going to take place. Contamination can happen. Shifting from one place to another place was obviously a problem. So Then at that point of time, it was decided that we should go for a solid-based definition. So like we are talking about redefinition a lot right now, but this redefinition is happening based on the requirement since the beginning itself. So from the first definition, within 8 years, we had a definition now from fluid-based to solid-based. And here, platinum cylinder was selected, which presently we know that cylinder is known as kilogram of archive, and it became the new mass unit. So now what happened is whatever was the weight of water at 4 degrees centigrade was chosen as the weight of kilogram of archive, right? So now it was defined in 1872 as equal to the mass of international prototype of kilogram, matching the kilogram of mass, kilogram of archive mass in 1872. So 1799 to 1872. So it is a quite a big time, around 70 years. So the definition, the first definition existed for 4 years. Then the reference temperature was changed to 4 degree. Then again, after 4 years, the definition was changed from fluid to solid, and then it existed for 70 years. And then again, because platinum was having some problem, so an alloy was made, platinum iridium alloy, which was there to improve the surface finish, the hardness, all those things, and the stability of the alloy with respect to the temperature. So keeping all those things in mind, the definition was again changed to a alloy, from a pure material platinum to an alloy. Now, parallelly, several other things were going on. The awareness was increasing. So a need was felt that we should have an international body which should have monitoring control of all the standards. So in the year being held, IPK was officially sanctioned as the definition of the kilogram. And in 1901, in the third CGPM, the definition which was adopted as kilogram is the unit of mass equal to the mass of the IPK. So whatever is the mass of IPK is going to be 1 kilogram. So this was the definition which was adopted in the third CGPM in the year 1901. So from 1901 to 2019, so almost for 120 years, this definition existed. And this is the definition which all of us know, even in the NCERT textbook also, this definition existed. However, even after we have a very stable alloy, still some variations were observed. So when IPK was compared with the kilogram of archive, it revealed some discrepancies. Then a special periodic verification was organized during this period from 39 to 46, and it was found that even the official copies, which we saw in one of the few first slides, official copies also gained several tens of micrograms relative to IPK. Now, this was the point where everyone was in a fix. This gain or this drift, we have to attribute it to which one, whether it has to be attributed to the IPK or it has to be attributed to the official copies. So there was a problem. There is a difference, there is a drift, but nobody knows to whom or to what we should attribute it to. So from this point onward, people started thinking about, again, the new definition, which should not be dependent on these things. So parallelly, there were other things also happening. So for the harmonization throughout the world, SI units were introduced in the year 1960. And when harmonization things came, the co-data was formed by the International Council of Science, which has a duty of managing scientific data and recommending constant. So since now you can see here from fluid to solid, now we are marching ahead for the constants based definition. So this was the beginning where we have this formation of co-data, and then the co-data created the task group on fundamental constants for periodic recommendations on the physical constant. So in 69, we got this task group on fundamental constant. Now, there was a paradigm shift in the year 1975 when Dr. Brian Peter Kibble, when he was while he was working in a lab on an entirely different problem, he came across with the idea of Kibble balance, where he demonstrated that we can have a linking between a mechanical power with the electrical power. And this Kibble balance, or this discovery, became the basis for the redefinition of mass. And you can see how much time it took from the discovery to its implementation. So it was discovered in 75 and was implemented in 2019. Then as we saw in the second verification, in the third verification also, mass change trend was found to be there with respect to the national prototypes. Then parallelly, like we were having advancement in the area of mass, we were having advancements in the other areas of metrology, for example, electrical standards. And then came Josephson voltage and quantum Hall resistance somewhere around the year 1990. And it enabled more precise measurement of the Planck constant. We will see how in the coming slide. So in the 20th CGPM meeting, which was held in 1995, third periodic verification results were reviewed, and it was considered that kilogram should be redefined and it should be based on a fundamental constant, which will be realized using Watt balance or XRCD method. I will talk about Watt balance, what it is, and XRCD method. Briefly, I will just mention. And again, in the 21st meeting, it was recommended that in the realization methods, Watt balance and XRCD method, we should go for refinements. We should work more so that we get a better result, so that it can be basis for the future redefinition. And the first proposal for redefinition came in the year 2005, which proposed using a fixed value of fundamental constant for the kilogram, though discrepancies delayed the change. So in the 2007 23rd CGPM, it urged progress in experiments for possible redefinition. And similarly, now the job of CCM, the Consultative Committee of Mass, was to define the conditions for accuracy, consistency, and traceability required for the redefinition. At one level, we were talking about the redefinition, but at the same time, we should maintain the status.
I'm sorry, ma'am, can I disturb you? Ma'am, actually, your slide of this 2007 to 2014 extraordinary coordination calibration, it is only visible.
It's not moving.
Yes. So the slide timeline focusing on some of the major developments and progress made over the years.
I think
Now it is 2014, 2019, 29. The last slide was 2019. Now, can you proceed? You are here only? You are speaking
Yes.
about the year, or you have crossed it?
No, this only I am speaking. Is it okay? Shall I continue?
Then it's okay.
Yeah. So it was okay. So it was important that we were getting traceability from international prototype of kilogram, and we were having a certain level of like it was having a zero uncertainty, and we were having at a certain level. So now with the redefinition, the idea was that we should not go far from that particular level. We should lie in that particular window where we are having the traceability from the international prototype of kilogram. So CCM gave us the conditions for the accuracy, consistency, and traceability required for the redefinition. And in the next meeting, that is 24th meeting, it was decided that the definition is going to be based on Planck constant, because when we talk about XRCD method, there was it will directly find out the Avogadro number. So there was a talk that we should have a definition based on Planck constant or Avogadro constant. So finally, it was decided that we will have a definition based on consistency, Kibble balance, and silicon sphere method was compared. My slides are visible?
No, ma'am.
Okay. So in the next meeting, the CGPM urged that we should try to complete the experiment as soon as possible so that the new definition can be adopted. And a timeline was given to CoData that by 2017, the final value of the Planck constant should be declared and it should be frozen. So in 2017, CoData updated the final constant for redefinition. And then in the 2018 CGPM, the kilogram using Planck constant was redefined. And it was implemented on 20th May, which is a historical day for all the new definition of kilogram. Now let us try to summarize everything. So where we started, mass difference between the official copies and IPK was found to be more than 50 microgram.
Hello.
Drifted.
Ma'am, your slide is not visible.
Slide is not visible.
Yes, ma'am.
Let me try to share again then. Is it okay now?
Yeah, now it is okay. Yes, ma'am.
Okay. So this was the problems from where we started, that there is a drift of 50 microgram between the official copies and international prototype of kilogram, and we do not know whether we should attribute this drift to IPK or to the official copies. Similarly, in case of NPK 57, it also showed variation For the first calibration, this was the value. After the redefinition, the value became this. I'll come to the graph in a while. And then the variation in NPK was retuned considering the offset in IPK. So now you can see here in this graph how value of official copies varied with respect to IPK. You see how it has changed over the years. So this definition is not time invariant. Similar effect was observed in NPK also. We can see here how with time it is changing. Okay, so this is the reason why finally it was decided that we should go for a definition which is going to be based on a fundamental constant and it is not going to change with the time. So at the 26th CGPM meeting in Versailles, new definition for kilogram was adopted and it was implemented. And what is the new definition? The kilogram symbol kg is the SI unit of mass. It is defined by taking the fixed numerical value of the Planck constant h to be 6.62607015 into 10 power minus 34 when expressed in unit of joule second, which is equal to kilogram square meter per second, where the meter and second are defined in terms of speed of light and hyperfine frequency of cesium. And the value of Planck constant is equated with respect to kilogram using this equation. Now, if we talk about what are the methods by which we are going to realize this definition. Now, once we have a definition, we need to realize that definition. How we are going to realize? So there are two methods presently, mostly worldwide. So one is XRCD method and the second one is Kibble balance. I will be discussing about Kibble balance technique because we are working at CSIR NPL on the Kibble balance, and we have developed demonstrated a model, demonstrated this this definition using a model for 1 to 10 gram, and presently we are working on 100 gram Kibble balance. Now, how it has affected the traceability now, because as a consumer, we are more interested to know what is the effect of this redefinition, how it is going to affect us. So there is whatever change is there, it is at the apex level. When we are coming down, there is no change and there is no effect on the consumer. So this one point at the time of redefinition, I heard people talking that kilogram itself has changed. Now the value of kilogram is changed. So how it is going to happen? No, nothing has happened at the consumer level. Whatever has happened, whatever change has happened, it has happened only at the apex level. So apex level, we have now Planck's constant, and then we have consensus value. I will talk about it, what it is, consensus value. And then we have primary mass standards and then secondary mass standards. So this is how we are having the traceability of mass. So here is a picture of Dr. Brian Peter Kibble, who is behind the this new definition, and mass is defined in terms of this equation. This equation looks very complicated. Principle is very simple, but the Kibble balance, making Kibble balance is a very complicated thing and it requires interdisciplinary expertise. I will be talking about it in a while. So yes, so now let us see, try to understand. So at the apex, after the redefinition, we have Planck constant. So Planck constant, practical realization of the definition of the kilogram. Okay. Now in between we have consensus value. So we are getting the traceability from Planck constant, but we are disseminating the mass value using the consensus value. And using this consensus value, now at present, NPK 57 is having uncertainty of what, 2 microgram, and then our transfer standards are having 53 and 56 for the working standard. So now let us try to understand the principle of Kibble balance. So if we talk about understanding the principle, so if we have a 2-pan balance, okay, and at one pan we are keeping, let us say, 1 kilogram, and then here a shopkeeper will keep on adding small amount till these 2 pans are balanced together. So this is how we are doing the measurement using 2 pan. Now in Kibble balance, we have an unknown mass here. Now this pan where we are keeping a known mass, known weight, has been replaced by a coil and a magnet. Okay, so now we have a current carrying coil which is placed in a magnetic field. So what it does, Kibble balance, it compares virtual mechanical power to virtual electrical power. Okay, and it is linked to Planck constant by 2 quantum phenomena, that is quantum Hall resistance QHR and Josephson voltage standard JBS. Now further trying to understand how it operates. So it operates in 2 modes. So one mode is known as static mode or force mode. Another mode is known as dynamic mode or velocity mode. As you can see on this screen, this is our force mode or static mode, and this is our dynamic mode or velocity mode. Now how it operates? So now we have a mass kept on a pan. So the force acting on this mass is going to be mg. Now, as I explained just now, that we have a current carrying coil and it is kept in a magnetic field. So we have 2 pans here which are suspended. Let us say we have a knife edge here. So now the force acting on this current carrying coil is going to be equal to the current which is flowing into it, the magnetic field, and the length of the coil. So we have 2 forces right now. One is electrical, another one is mechanical, and our job is to make these 2 equal so that they get balanced. So once these 2 forces are going to be balanced, what we will have as a final thing, mg is equal to IBL. When both the pans are balanced, that means both the forces are getting equal. So when both the forces are going to be equal, we can write very safely mg is equal to IBL. If we write this equation, rewrite this equation in terms of BL, so BL is equal to mg over I, right? So this is one equation which found from the static mode or the force mode. Now let us come to the dynamic mode or the velocity mode. Now what we do here, we replace the mass. There is no mass on the pan, and these 2 balances are these 2 pans are balanced. They are in the equilibrium position. Now once they are in the equilibrium position, one pan, this pan is moved, let us say, with a velocity v. Okay, now when it is moving with a velocity v and we have a coil placed in a magnetic field, so what will happen? There will be a induced voltage. So now this induced voltage is going to be equal to the magnetic field, the velocity with which it is moving, and the length of the coil. So now U induced voltage is equal to BLV. Now, so this is our equation. Now this equation can be rewritten as BL is equal to induced voltage divided by the velocity of the coil with which the coil is moving, right? Now we can see equation 2 and equation 4, BL is common. Okay, so now these 2 equations can be equated provided length of the coil, magnetic field, their alignment do not change when we change the mode from static to dynamic, right? So when we are going from static to dynamic, nothing should change which will change the value of the BL. So value of the BL should remain same in both the modes. So when the value of BL is going to remain same in both the modes, we can very easily equate the right hand side of equation 2 with the right hand side of equation 4, which is UI is equal to mgv. Okay. So now again rewriting this equation in terms of mass. So UI divided by GV. So mass can be now written in terms of voltage, current, velocity, and the acceleration due to gravity of that particular point where we are doing this measurement. So now mass is going to be dependent on these parameters. Now we are talking about that these are quantum standards. So how the quantum standard is playing a role in Kibble balance. Okay, so how it is happening? So at this point, when we are having this equation, we introduce quantum standards for voltage and current. So now from where it is coming, as I explained in my earlier slide, that Josephson voltage standard is used for the voltage. So it is defined, voltage is defined in terms of this in the Josephson voltage, where the Klitzing constant is Josephson constant is equal to 2 multiplied by the elementary charge divided by the Planck's constant. Similarly, when we talk about the quantum Hall resistance, resistance can be written as 1 over I h divided by square of elementary charge, right? So now here we have voltage, so we can use this equation, and here we have I, current. Now current can be rewritten in terms of voltage and resistance, so that we can use this part also. So using this equation, and this equation, all three equations, finally we can write mass in terms of Josephson constant, Klitzing constant, the induced voltage, the current, acceleration due to gravity, velocity. So all these factors are going to play an important role in the value of mass, which we are going to, unknown mass, any unknown mass we are going to measure. So now using this, it is going to be a value. Now it can be measured anywhere, anytime, it will not change. Okay, so by using this definition, now we have time invariant definition, which will not change with time. And the method of realization, which we talked about for doing that, is Kibble balance. And there are, I will be in the next slide, I will be showing there are some NMIs who are working on XRCD method also. So if you see here, okay, so I mentioned about co-data. So how the value of Planck constant came into the picture, how the value of Planck constant was frozen. So those NMIs who were able to develop fully functional Kibble balance, they participated in key comparison. And there was a traveling standard which was going from one place to other place, and they measured, like for example, NRC measured, NIST measured, LNE measured. They all measured the value of Planck constant, and finally the Planck constant was frozen, and the value of Planck constant was decided to be this, within relative uncertainty of this. Okay. Now, this was at the time of measurement. Now, since it is going to be a fundamental constant, it cannot have a uncertainty. So presently we have Planck constant without any uncertainty, and whatever uncertainty was associated with the measurement of Planck constant was assigned to IPK, which was existing with zero uncertainty before the redefinition. And that is why the value of our national prototype or for that matter, other countries' national prototype were retuned after the redefinition, because we were getting traceability at that point of time from IPK. So now this is the world map, and we can see here the NMI who are working in Kibble balance. So all the NMIs who are shown with blue, they are working in Kibble balance. Either they have full-fledged Kibble balance, or they have started working, or hardware is existing. They are doing some work towards the development of Kibble balance. And NPL India is one of those countries where we are putting our effort to develop Kibble balance for the country. Then PTB and NMIJ, Japan, Germany, these two NMIs, they are working on XRCD method. And then China is working on Joule balance. So now I talked about consensus value. So what is consensus value? Let us try to understand that, and how we are disseminating, the mechanism of dissemination of kilogram. So it is divided into 4 phases: phase 0, phase 1, phase 2, and phase 3. So phase 0 was effective before 20th May 2019, where the traceability was drawn from international prototype of kilogram, which was having a 0 uncertainty. And all the NMIs were putting an effort to measure the value of Planck constant. And our national prototype of kilogram, other countries' national prototype of kilogram, they were traceable to international prototype of kilogram, which is kept at BIPM, which we saw in the initial slides. So this was the phase 0, and it was the condition before the redefinition. Now came the phase 1. Now phase 1 was effective from the day of new definition of the kilogram, right? And it will remain effective till the approval of consensus value from the first key comparison. So let us try to understand here. The first key comparisons which happened were to find out the value of Planck constant. Now once the value of Planck constant is fixed, then the next key comparisons happened for finding the consensus among the NMIs who are participating in the comparison, so that we have a consensus value. So the key comparison is held among the NMIs operating the Kibble balance or XRCD, and during this period, IPK will have an uncertainty of 10 microgram. So from 0 uncertainty, IPK was assigned a uncertainty value of 10 microgram, and then phase 2, presently we are in phase 2. Now what is the difference between phase 1 and phase 2? So now phase 2 is from 1st February 2021, and in this regime the traceability will be taken from H and dissemination from the consensus value, and this will end when the realization technique refined itself to an extent that consensus value will no longer be needed. And CCM has decided that the standard uncertainty of the consensus value is 20 microgram. So now we are getting our dissemination from consensus value. So 20 microgram due to the consensus value is added in our uncertainty, which is assigned. So one is whatever measurement they are doing, that 20 microgram is the contribution from the consensus value. And finally, the third phase, this will be when after the key comparison, when the value of the mass which we are realizing using the comparison method comes in a narrow window which is acceptable or which is defined by the CCM, then there will not be any need of consensus value. And at that point of time, the NMIs who have participated in all these key comparison can directly give you the traceability. So presently, like we were going to BIPM, every 10 years to getting the traceability. Now we are having traceability using the consensus value. Once we are in phase 3, then there is not a mandatory requirement for us to go to BIPM for getting the traceability. Any NMI which has participated in the key comparison, maybe it is NIST USA or PTB Germany or NMIJ or NPL UK, we can approach to them and get our national prototype calibrated and maintain the traceability and disseminate in the country. So this is applicable for those NMIs who are not having their own Kibble balance. And we also lie in that category where we are not having any Kibble balance, full-fledged Kibble balance from where we can provide the traceability. So this is the table of graph of the consensus value. So now we can see that the comparison was organized by BIPM, and there were total 9 participants who participated in this key comparison: BIPM, France, Switzerland, USA, Canada, and Turkey. They participated with Kibble balance. China participated with Joule balance, and Japan and Germany, they participated with XRCD method. And this is the kind of values and the associated uncertainty which has been obtained. Now, differences between the mass values attributed to 1 kg standard using the realization experiment of the participant and the key comparison reference value with associated uncertainty is shown here in this. And this particular point is our IPK, which is getting the traceability from the Planck constant. So this is the value. Now, what I was telling in my previous slide, phase 3 when it will come. So the deviation between the values coming from this NMI should be as low as possible, so that we no longer require the consensus value. So this window has to be very small. Right now there is a scatter, so we will be in phase 2 till this scatter can be minimized, and NMIs are working in that direction. So this was the story, the history of mass and the method of realization. Now I will be talking about CSIR NPL. So how we are moving in that particular direction. So as I explained that we have started with 1 to 10 gram, and our start was very, very modest. Everything, whatever you can see on the screen, was fabricated in our own workshop. So this is the design which NIST USA has adopted. So they have a wheel, and from this wheel we have 2 pans. You can see the pans hanging here. This is our current carrying coil, and we pasted a magnet here. Although this current carrying coil should be completely immersed in a magnetic field. So there was some problem. So we had a coin magnet pasted here so that we can have a magnetic field, and the coil was moved here, and we have a laser sensor which is monitoring the position. Then we had a LabVIEW program, a program made in LabVIEW, fully automated program. So we were measuring the induced voltage, current, the velocity, everything. And we were able to demonstrate the principle of Kibble balance using this indigenous setup made in NPL itself. Now, the knowledge which we gained for the demonstration, we utilized that knowledge for our present project, which is on which we are working. So our idea is presently to have a Kibble balance which can be used up to 100 gram, which should be able to realize up to 100 gram. And at present we are trying to have an uncertainty which is 1% or better. So once we are able to achieve that, then we will start refining our setup so that we can improve our uncertainty. And also we are trying to measure the Planck constant experimentally accurate enough, which as close as of the fixed value of the Planck constant. So for this purpose, what we have done, we have used a two-pan balance. You can see here this beam, and we have two pans hanging here. So for modifying this two-pan balance, we have removed the pan from this position. You can see a hook here. So we have removed these pans and retained this portion as it is and modified the pan portion, which I'll be showing in the next slide. So now you can see here, the top portion is same as the existing balance, and the bottom portion we have modified. Now one by one I will be mentioning about the parts of this balance which we have used or modified or utilized. So this is the balance from Ortling, and it has been modified. The first thing which I would like to mention about is the coil former. So what is the coil former? You can see here, this area, this is the coil former. This is made up of Hylam rod, and it is having two coils. You can see here, top and bottom, two coils. So primary windings and secondary windings. Okay, so now we have two coils, and how we are utilizing it, I will be talking about it in the latter part of my slide. Then the second important part for the Kibble balance is the magnet assembly. So now you can see a rod here. So we have ring magnets fixed here, and these ring magnets, we are using neodymium iron boron ring magnets, and they are arranged in alternating polarity. So we have a set of magnets in the top and set of magnets in the bottom, and in between we have a air gap, and we are moving the coil in this air gap. Okay, now the third point is our current source, programmable current source, which we are using for providing current to our coil. Then the next instrument which we are using is a function generator. Now what it does, it is providing a AC voltage to the secondary winding. Now when the AC voltage is provided to the secondary winding, because of the sinusoidal wave, the coil is moving up and down in the dynamic mode measurement. So this function generator is utilized for providing velocity to the coil. The next thing is laser sensor. It is very important. Now laser sensor is placed just below the pan, and we have a reflecting surface. You can see a sheet here. It is a reflecting surface which laser sensor is detecting, and we are knowing the exact position of the pan. So when it is moving, it will show us display the difference between the initial position and the position where it has gone. And then finally everything has been automated using our NIPCI DAC card and a terminal box, and using a LabVIEW software where we are having data acquisition with the help of DAC card and the BNC terminal box. So this is the setup which we have developed, and we are still modifying the setup so that we can have better and better results. So now when I was explaining Kibble balance, how it works, so I talked about dynamic mode and I talked about the static mode. So in the dynamic mode, we are providing input signal, and now this 6 mm is what? This air gap which I just talked about. So these are set of magnets. We can see the top, we can see the bottom magnets, and the top magnet is under the coil. So, and there is an air gap there is an air gap. In this air gap, the coil is moving, and the induced voltage is measured from here with the help of a terminal box. The displacement is again measured with the terminal box, and with the GPIB, it is going with the help of DAC card. It is going into the PC in a software which we have prepared using the lab tool. So you can see here the so that was the flow chart. Now here you can see these are the wires which are going. These are the wires, and then how it is connected to the BNC. You can see here laser is connected here. The waveform generator is connected here, and so on and so forth. And then finally this BNC is connected in this CPU, which is having a DAC card, and we have our own software which is recording the data. And this is the complete setup. So now the function generator, as I mentioned, that it is providing us a sinusoidal wave. So we are giving an input of Vs, that is the supplied AC voltage. Vs0 is the amplitude of the supplied voltage. Sine omega t plus phi. Omega is the angular frequency of the supplied signal, and phi is the phase of the supplied signal. If there is any phase difference, it will be mentioned here. Now, what is omega? Omega is 2 pi f, and f is the frequency of the supplied signal. And frequency which we are using is 100 millihertz, and the amplitude of the supplied voltage we are utilizing for this particular measurement is 29 millivolt. So the kind of signal output which we are getting is U, that is induced voltage in the coil, is equal to U0. U0 is what? Amplitude of the induced AC voltage in the coil, sine omega t. Omega I have already mentioned, explained what it is. Okay, so first is our induced voltage. Now second point, using the same input parameter which we are recording, is the displacement. So what is the displacement? Y is the vertical displacement of the coil. Y0 is the amplitude of the displacement of the coil, and phi y is the difference in the coil with respect to the induced voltage. So if there is any phase difference, it is recorded in terms of phi y. So these are the two outputs which we are getting when we are giving this input. Now keep this image in mind. Here we are recording the value of the displacement. Now what we exactly want? We want velocity. Okay. So now using the same input, we got the velocity. Now we are calculating the we got the displacement. Now we have to calculate the velocity. So output is calculated from this displacement. So here we have this equation, y is equal to y0 sine omega t plus phi y. So what is velocity? If you differentiate this dy by dt, it will give us the velocity of the oscillating, and that is plotted here. So this is how we are getting our output signal. Now using this output signal, now we are calculating the value of our geometrical factor, which is BL. So U by V. So U0 sine omega t, we can just substitute the value which we are using in the input signal, Y0 omega cos omega t. So here you can see Y0 omega cos omega t, and here you can see U0 sine omega t. So utilizing these two, we are finally finding the value of the BL. And now which is the velocity which we are using? It is the peak value. So peak value of BL obtained from dynamic mode measurement for coil velocity is this, and it is the average at the peak value. So this is how we are measuring the value of BL in the dynamic mode. Now using the same BL value which we have obtained, and the value of G, which is applicable for NPL, we are calculating the current which is required for measurement of the mass for 1 2, 5, 10, and 20. So we have measured these mass values, and the relationship is shown here. Now, when we are doing a measurement, then there is going to be an associated uncertainty with these measurements. So we have dynamic mode equation U is equal to BLV. So what we can do is we can just do partial differentiation of this equation with respect to the induced voltage for finding out the uncertainty in the measurement of BL. So if we rewrite this equation in terms of BL, so BL is equal to U by V. So one, we will be differentiating with respect to induced voltage, and then again we will be differentiating it with respect to the velocity. So finally we are getting an equation of this form where C1 and C2 are the sensitivity coefficient with respect to the delta V, that is delta U, that is induced voltage, and delta V, which is the velocity. Now similarly we will be finding the uncertainty in velocity. So velocity is dy by dt. So putting all the values and then differentiating it with respect to y and with respect to t, we will be finally getting an equation C3 delta y and C4 delta t, where delta y is the delta y0 is the C3 is the sensitivity coefficient for delta y0 and C4 is the sensitivity coefficient for delta t. So final uncertainty equation which we are going to get is this, and using this equation we are able to calculate the value of BL with respect to the uncertainty which we have calculated. So similarly, we are going to have an equation for static mode. So M is equal to 1 over G, and we have a function of BL and I. And if we are differentiating this equation with respect to BL and with respect to I, we will be finally getting an equation which is giving us two sensitivity coefficient for BL and I. Now this BL we have already calculated using our dynamic mode. So we utilizing that, now we will be having uncertainty due to BL, uncertainty type A uncertainty due to current, and type B uncertainty due to the current. So finally we will be having, this is the final uncertainty equation which we have utilized for calculating the uncertainty. This table gives us the uncertainty budget for 1 gram, 2 gram, 5 gram, 10 gram, and 20 gram for all the parameters which I have just discussed in the previous slide. And the final value of the calibrated mass along with the uncertainty at k is equal to 1 is shown here. This is a very coarse value which we have achieved with this setup. So a lot of work is required to be done in this setup. The first thing which we noticed is that the value of BL which we are getting is 2.7, and which is only sufficient for us to measure up to 20 gram. Since our objective is to go up to 100 gram, so we have modified the coil former. We have modified the magnet assembly so that we can increase the BL value maybe by to a large extent, so that we can go up to 100 gram. So presently the modified setup in which we are working, we are able to achieve BL value up to 12. With that we are hoping that we will be able to go up to 80 gram of measurement, and then now we know what extra we need to do, what extra needs to be modified so that we can achieve 100 gram. So it is an iterative process in which we are moving ahead, and hopefully by end of this year or maybe middle of next year we will be able to measure up to 100 gram, and we can have at least uncertainty budget and a coarse value at least less than uncertainty, 1% uncertainty we will be able to measure. And this is the team. Our director is supporting a lot in this measurement, and Thomas John sir, who is ex-chief scientist of NPL, and he is continuously supporting us in electrical measurement. And these are the students who are contributing continuously towards the development of Kibble balance for NPL India. Thank you so much for your attention, and maybe we can have some questions if I can take maybe.
So very good, madam. So you have done your best presentation today. I think you are on the way to achieve the true value of the mass. What is desired to the country, that you are going in that very way.
Thank you very much, ma'am, for your brief and very interesting presentation. I would like to request you to kindly share this presentation with me so that I can share with all the participants, as well as we can place it on our website for the understanding and the knowledge of all the participants even after the program. Thank you very much, ma'am. Thank you. I'd like to request all the participants to kindly switch on your video so that we can take few photographs for our social media platforms. It was a wonderful topic, and certainly we have to work together for the development of these Kibble balances in our country. This is a new future of the mass metrology.